Okay. Hello, everyone from the globe. I'm Bahar Ali Akbarian, and I'm honored to moderate today's European session discussing one of the most pressing issues of our time, environmental pollution. The topic of environmental pollution has gained more attention in recent years as the impact of human activity on our planet becomes increasingly apparent. From rising sea levels, extreme weather conditions, and melting glaciers to deforestation and the mass extinction of a species, the consequences of environmental pollutions are undeniable. As we continue to emit greenhouse gases, pollute our waterways, and destroy natural habitats, we risk irreversible damage to our planet and our own survival as a species. Additionally, the ongoing pandemic has highlighted the interdependence of human health and the environment and underscored the urgent need for a more sustainable, resilient, and equitable world. Let us not forget that our actions today will shape the future of our planet and all those who inhabit it. As the continent, Europe has been at the forefront of the fight against environmental pollution. European nations have been actively pursuing policies to reduce emissions, promote renewable energy, and protect our natural resources. The European Union has set ambitious targets for reducing greenhouse gas emissions and promoting sustainability in all sectors of the society. Despite the progress made, we still face enormous challenges in mitigating the effect of pollution on our environment. In many parts of Europe, for example, air pollution level remains dangerously high, causing serious health problems and reducing the quality of life for millions of people. Water pollution, soil degradation, food waste, plastic residues, and the loss of biodiversity continue to threaten ecosystems and natural habitats. Climate change, driven by greenhouse gas emissions, is already having severe impacts on our planet and will require urgent action to avoid catastrophic consequences. In light of these challenges, it's crucial that we come together to share our knowledge and expertise on environmental pollution. We must address the issue of food waste, which is a significant contributor to environmental pollution, as well as promote the use of renewable energy to reduce our reliance on fossil fuels and combat climate change. We must work collaboratively to develop effective solutions to protect our planet and secure a sustainable future for all. Throughout the contributions of our distinguished speakers today, I'm confident that we will make great strides in addressing this critical issue. During this session today, our first speaker, Dr. Kazatsa, will discuss a new macro phytodepuration process to remove emergent contaminants from wastewater. Our second speaker, Professor Converti, will talk about a process behind the production of a renewable energy. He will share his research on the advancements in an anaerobic digestion process to upgrade biogas to biomethane. Our third speaker, Dr. Trucillo, will introduce sustainability indicators to develop green processes. He will talk about the importance of promoting circular economy for sustainability and will show a process to evaluate the sustainability metrics. The last two presentations will focus on the food waste issue and the solutions to tackle that. Dr. Pettinato will share her research on a new technology platform to valorize food waste using green processes. And finally, our last but not least speaker, Dr. Ferrari, will talk about a process to repurpose food waste to produce valuable products for biomedical applications. Together, these speakers represent a diversity of perspectives and expertise on environmental pollution in Europe. Their insights and experiences will provide valuable insights into the challenges we face and the action we can take to address them. I hope you are all as excited as I am to hear from these esteemed speakers, and I invite you to join me in thanking them for sharing their time and expertise with us. So let's get started. Our first speaker is Dr. Alessandro Alberto Casazza. He is assistant professor at the Department of Civil, Chemical, and Environmental Engineering of the University of Genoa in Italy. He is co-founder of the Interdepartmental Research Center, Biologically Inspired Engineering in Vascular Medicine and Longevity Belong since 2013. His research focuses on macroalgae growth and utilization for environmental purposes. His main research activity is documented by 90 scientific papers published in international journals and participations in different international conferences. Dr. Casazza, thank you so much for joining us today, and the floor is yours.
Good afternoon. Thank you, Bahar, for your introduction. I'll start with my presentation. Oops, sorry. Okay, can you see my presentation?
Not yet.
Now?
Yes.
The screen? Okay.
We're seeing the screen, yep.
Yes, okay. Okay.
Perfect, thank you.
Okay, thank you. In this presentation, we will see how emerging contaminants can be removed using microphyto depuration. An increasing urgent problem is the high production of wastewater. In fact, in the most industrialized country, this value is higher than 100 cubic meters per person every year. There are two types of wastewaters, domestic and industrial. Domestic wastewater comes from houses and apartments, while industrial comes from manufacturing or chemical processes. The quality of this waste depends on their source, the way in which they are collected, and the treatment they receive. The final fate of this waste is also very different. In general, the wastewater use after the pollutant removal is very low in the greater part of the world. The potential for industrial wastewater reuse is dependent on a variety of factors and differs from one industry to another. Innovative industry water purification technologies make it economically feasible to convert all kinds of wastewater back into purified, reusable state. And after treatment, this water once again becomes an asset instead of a potential financial and environmental liability. The pollutants normally present in wastewater are those listed in this slide. As you can see, we can find organic matter, inorganic nutrients, pathogenic and non-pathogenic microorganisms, heavy metals, chemicals, and solids. But it is necessary to consider the presence in wastewater of so-called emerging contaminants. These are chemicals that have been recently detected in the environment and are of growing concern due to their potential effect on human health and on the environment. These contaminants can include a wide range of substances, such as pharmaceuticals, personal care products, pesticides, and industrial chemicals that have not previously been widely studied or regulated. They can enter the environment through a variety of sources, including wastewater treatment plants, agricultural runoff, and industrial discharge. Emerging contaminants pose a significant challenge for environmental regulators, as their potential risks are often not fully understood, and there may be limited data available on occurrence and behaviors in the environment. It is difficult to provide correctly the amount of water that is contaminated by emerging contaminants, as the extent of contamination can vary greatly depending on the location and the specific contaminant in question. However, studies have shown that emerging contaminants can be found in a wide range of water sources, including, for example, groundwater, surface water, and drinking water supplies. In some cases, the level of emerging contaminants detected in these water sources may be cause of concern, as they can potentially pose risk to human health and to the environment. Here are some examples of water polluted by emerging contaminants. We can find in drinking water pharmaceuticals. In fact, in many parts of the world, pharmaceuticals such as antibiotics, hormones, and painkillers have been detected in drinking water sources. Microplastics, that are small plastic particles, can be found in aquatic ecosystems, including rivers, lakes, and sea. They are a growing concern due to their potential impacts on aquatic life and the potential for them to enter the food chain. And polyfluoroalkyl substances, that are a group of industrial chemicals used in a wide range of products, including 5,5-T foam, have been detected in groundwater in many parts of the world. Regarding pesticides, these compounds are widely used in agriculture and can enter surface water through runoff or spray drift. Some pesticides have been found to have negative impacts on aquatic life and can also pose risks to human health. And personal care products can be found in wastewater. Shampoo, soap, and sunscreens contain a variety of chemicals that can enter wastewater treatment plants and potentially be discharged into surface water. Luckily, some techniques can be used to remove this pollutant. For example, activated carbon can be used to remove organic compounds, including many emerging contaminants. It works by absorbing the contaminants onto its surface. Ozonation involves adding ozone to water, which can break down organic compounds and eliminate emerging pollutants. This process can be particularly effective for removing pharmaceuticals and chemicals from personal care products. While with reverse osmosis, we can filtrate emerging contaminants. It involves forcing water through a semi-permeable membrane that only allows water molecules to pass through, while blocking larger molecules and contaminants. The UV treatment can be used to destroy organic compounds. This process involves exposing water to UV light, which can break down the molecules and contaminants. Advanced oxidation process involve using a combination of chemicals and UV or ozone to break down compounds and removing emerging contaminants from water. These processes can be particularly effective for removing complex mixture of pollutants. It is important to note that the effectiveness of these techniques can vary depending on the specific contaminants and the water source in question. In some cases, a combination of different techniques may be necessary to effectively remove emerging contaminants from wastewater. In addition to chemical and physical methods, biological treatments can also be used to remove emerging contaminants from wastewater. Here I reported some example, biodegradation, that involves the breakdown of contaminants by microorganisms, which convert the compounds into less harmful substances. This can be achieved through a various biological treatment systems, such as activated sludge, constructed wetland, or biofilter. And phytoremediation, that involves the use of plants to remove contaminants from soil and water. Plants can absorb, metabolize, and break down contaminants, including some emerging pollutants, through various mechanisms such as phytotransformation and phytostabilization. It is important to note that the effectiveness of these methods can depend on the specific contaminants and the condition in which the biological removal process takes place. Some emerging contaminants may be more difficult to biodegrade than others, and the presence of other compounds in wastewater can affect the performance of the biological treatment system. An increasingly studied biological method is microphytodeporation. This is a biological water treatment process that uses microalgae to remove organic pollutants and nutrients from water. Algae grow quickly and can be harvested for the production of biofuel or used as animal feed. So the microphytodeporation process can also have added value in terms of producing new raw materials. The microphytodeporation process can be used to treat various types of wastewater, such as those produced by the food industry, agriculture, and human sewage. However, this process requires careful management of microalgae cultivation in order to maintain an adequate balance between nutrients, biomass, and pollutant removal. But what are microalgae? Microalgae are unicellular microorganisms with a dimension around 1 to 5 micrometers. In the nature exist more than 200,000 species with peculiar characteristics, different growth conditions, and morphology. Some examples are reported in this picture. As you can see, they show different shape and color, and they change the intracellular composition. In fact, depending on the growth condition and on the microalgae species, the percentage of lipid, carbohydrates, and protein that present the main intracellular components is completely different. Moreover, an important factor that can modify the microalgae cell composition is their metabolism. In fact, as reported in this slide, microalgae are able to grow in autotrophic conditions using carbon dioxide and light for their metabolism through the photosynthesis process. Or they can grow in heterotrophic conditions using organic carbon as nutrient source. The microphytodeporation process involves the cultivation of microalgae in dedicated cultivation tanks, where algae absorb nutrients such as nitrogen and phosphorus and simultaneously remove pollutants such as organic compounds. Microalgae can be cultivated in systems called photobioreactors. In this slide are reported some laboratory-scale photobioreactors located at the Environmental Biotechnology Lab of the University of Genoa. Usually at industrial scale, microalgae can be cultivated in closed or open systems, and this configuration presents different downsides and advantages. For example, the open system requires an easy management, but the culture can be contaminated by other microorganisms, while the closed system, photobioreactors, requires qualified personnel to work with it, but have a higher surface exposed to light, allowing to reach a higher biomass concentration. Considering that a significant cost for the industrial microalgae cultivation is related to the use of huge amount of fresh water and salt, the microalgal synthetic grow medium could be replaced with wastewaters. Compared with other wastewater treatment, microalgae-based process display different advantages, including efficient and simultaneous nitrogen and phosphorus removal, no requirement of additional chemicals, oxygen generation, carbon dioxide mitigation, and potential values added product from harvested biomass. As concerns emerging contaminants treatment, microalgae can remove these compounds using 3 different mechanisms. With bioabsorption, that is a passive process in which soluble compounds are distributed between the liquid phase and the cell wall, or the extracellular polymeric substances of microalgae. Unlike bioabsorption, bioaccumulation is an active process that consumes energy and is relatively slower than the absorption process. Along with nutrients, microalgae can uptake and accumulate pollutants within the cell. And biodegradation is a metabolic degradation or breakdowns of compounds catalyzed by enzymes. Generally, microalgae turn complex parent compounds into simpler compounds. This process might involve several enzymatic reactions. The treatment of wastewater containing antibiotics is very complex because this wastewater contains not only antibiotics but also inorganic and organic compounds, which altogether can inhibit the activity of microorganisms in wastewater treatment plants. Conventional wastewater treatment plants are not primarily designed to treat biologically active substances. These are inadequately removed from the wastewater and thus enter the aquatic environment. If we consider scientific papers published since 2006 with topics related to the word microalgae, antibiotic, and removal, we can see that their number has exponentially increased in recent years. We found 70 articles in 2022 respect to only 3 articles in 2015. For example, the removal of ciprofloxacin and amoxicillin in different types of biological treatment plants can reach up to 59 and 76% respectively. However, the final concentration in treated wastewater are still problematic, as both antibiotics can occur in the aquatic environment at a concentration up to 0.4 milligram per liter. Although measured concentrations are generally many times lower than therapeutic dose and are not acutely toxic, but little is known about the long-term effects on aquatic organisms. In literature, various articles can be found regarding the treatment of antibiotics using microalgae. The pollutant removal yield vary not only depending on the microalgae used, but also based on the antibiotic concentration and operating conditions, such as temperature, lighting, and the type of photobioreactor. Generally, the methodology primarily employed for the removal of this tested antibiotic has been biodegradation. This is an advantage process compared to bioaccumulation and bioabsorption, since the emerging pollutants is definitively removed from the water and the microalgal biomass, This led to hypothesize multiple scenarios for the use of the biomass collected downstream of the treatment. In order to increase the efficiency of removal of emerging pollutants, it is possible to hypothesize the use of multiple technologies simultaneously. For example, the combined use of microalgae and UV treatment has been studied, and it has been found that the removal of antibiotics is close to complete. The effect of UV partially degrades the chemical compounds which are subsequently fully absorbed or degraded by microalgae. This hybrid system can be proposed as a treatment system downstream of traditional wastewater treatment processes, before discharging the water into the sea or surface area. In fact, a possible solution to reduce antibiotics still present in post-treatment wastewater could be to install a microalgae grow system downstream of the treatment plant. Considering that microalgae can also purify gaseous effluent by removing and consuming carbon dioxide for photoautotropic growth, and moreover, at the outlet of the plant, in addition to purified water, we can obtain oxygen and microalgal biomass. For the treatment of emerging contaminants, photobioreactors with new configuration are being studied in order to maximize the removal efficiency. High-rate pond and stirred tank or plain and tubular photobioreactors, but a promising growth system is membrane photobioreactor. Harvested and scale up of the system are very easy, and it is suitable for wastewater treatment. Moreover, membranes provide a second line of antibiotic removal from wastewater. It is interesting to consider that the growth of microalgae in the presence of antibiotic resulted in a modification of the intracellular composition. Authors reported an increase in the lipid fraction of the dry biomass compared to the control growth. In some cases, the lipid percentage even doubled its concentration at the expense of the protein fraction. And after the growth, the microalgal biomass can be collected and used for the production of biodiesel. With a biomass particularly rich in lipids, this can be extracted and converted into biodiesel by transesterification. Another possibility, in order to always have a good amount of biomass in the purification plant, is that lipid can be extracted through non-destructive extraction. This process, called microalgae milking, involves the periodic collection of compounds produced by microalgae, without killing the cell from which these compounds were extracted. In this way, microalgae can continue to grow and produce new compounds, maintaining their metabolic activity. This process has been developed as an alternative to the complete harvesting of microalgae, which can be expensive and require a lot of energy. Moreover, the periodic collection of compounds produced by microalgae through the microalgae milking process can increase the efficiency of biomass production and the production of high-value compounds, such as biofuel. The exhausted biomass downstream of the extraction process can be used to produce biofuel or chemicals through thermal treatment in absence of oxygen by pyrolysis. The pyrolysis process can indeed lead to the production of a gas, a liquid, and a solid that can be used as fuel. Another possible use of exhausted biomass is to convert it into material for absorbing pollutant molecules, further improving water purification. And so, in conclusion, we can say that microalgae can be successfully used for the depuration of different emerging contaminants, and it is crucial to study the water residence time inside the photobioreactor to ensure proper reduction of pollutant, while avoiding washing out of the microalgal culture. Research studies must be focused on the development of new photobioreactors configuration and on the reduction of process costs. The produced biomass can be employed for the production of new biofuels or new bioabsorbents. Thank you for your attention.
Great. Thank you so much, Dr. Casazza. It was very interesting. Is there any question from the audience? I'm also checking on the Whova. I'm not seeing any specific question, but yeah. Thank you, Angie.
Thank you.
Yep. If no, I just have a curiosity. Like, have you thought about the application of microalgae for removal of nano or microplastics?
Yes, there are a lot of papers on this topic. In our laboratory, we don't work on this topic because it is very difficult to quantify and characterize macro and nanoplastic. But we are working now on the removal of heavy metal and antibiotics. But it is an interesting topic, and microalgae can degrade nanoplastic. It is not so easy with microplastic, but with nanoplastic, yes.
Thank you. And there is a question from Vanji. She's asking, can the antibiotics be removed?
Excuse me, antibiotics?
Can they be removed from the water by microalgae?
Yes, antibiotic can be removed and biodegraded. So microalgae degrade molecules, and in the final biomass, we don't find antibiotics.
So they metabolized antibiotics.
Yes.
Great. Thank you so much. Any other question? We have a few minutes. Great. So thank you so much, Dr. Casazza, for your interesting topic. Thank you.
Thank you. Bye.
Bye. Okay, we have time, but I see that our next speaker is present, so we can move forward. So our second speaker is Professor Attilio Converti. Professor Converti is a full professor of chemistry and fermentation biotechnology at the University of Genoa in Italy. His research interests in the field of environmental biotechnology include anaerobic digestion, carbon dioxide capture, biogas upgrade, wastewater treatment with microalgae, photobioreactor design, and microbial remediation of polluted soils. He is author and co-author of more than 400 scientific publications in international journals. Thank you so much, Professor Converti, for joining us today, and the floor is yours.
Thank you very much, Bar. You are very kind, and I hope to see you, to meet you in Genoa as soon as possible.
Thank you.
Some information about the anaerobic digestion. It is a process of stabilization of the organic fraction of waste, which is performed by anaerobic microorganisms. The transformation that anaerobic digestion is able to do in a polluting material is a mineralization, which is the degradation to non-degradable substances, as gasification, i.e. a conversion of liquid or solid compounds, contaminants dissolved in water into gaseous products, and simultaneously a humification, which is the transformation of the decomposable organic material into a slowly decomposable material like the digestate or the digested sludge. Which waste we can treat through the anaerobic digestion. It may be a sewage sludge, an industrial waste, provided that it is sufficiently concentrated, an agricultural waste, or even the organic fraction of municipal solid waste. As an average, a biogas may have this composition. About three-fourths of the gas may be methane, from 2 up to 3 for 24% CO2, and the other gases are can be considered byproducts, hydrogen, nitrogen. Unfortunately, there is also the hydrogen sulfide, which is a problem because when we use the biogas to recover energy from combustion, the hydrogen sulfide is oxidized to sulfuric acid, and unavoidably will create some problems of corrosion of the engine. Another problem is the density of the biogas, which is much lower than that of air, which means that if we produce biogas and do not utilize it to recover energy, it cannot be released to the atmosphere. Otherwise, the biogas is able to reach the ozone layer, and unfortunately, the methane has a greenhouse effect which is about 40 times higher than that of CO2. In other words, if we decide to use anaerobic digestion, it is mandatory to utilize the biogas. One of the positive aspects of anaerobic digestion is that the stringent anaerobic condition are able to destroy some of organisms responsible for human diseases. For example, Entamoeba histolytica, Salmonella typhi, Mycobacterium tuberculosis, Escherichia coli, which are responsible for different diseases, can be effectively removed if we use adequate, sufficiently long residence time in the digestion. The anaerobic digestion consists of 3 stages that take place simultaneously if we are working under stationary condition in a continuous process, which is the most frequent situation, or in the following order during the startup of a new anaerobic digestion. The first stage is the liquefaction, the enzymatic hydrolysis of biopolymers, which are proteins, cellulose, starch, lipids. The products of liquefaction, the monomers of these biopolymers, are utilized by the so-called transition bacteria to make acidification. They are converted some volatile organic acids, the most abundant of which is acetic acid. And the third stage is the methanogenesis. A portion of the acidic products of the second stage are broken to give a mixture of carbon dioxide and biogas. However, there are other methanobacteria, autotrophic methanobacteria, able to utilize the hydrogen coming from the acidification to reduce directly the CO2 to methane. Therefore, we have 2 classes of methanobacteria. These are the schematic diagram of the degradation of the different biopolymers, the polysaccharides, lipids, and proteins, which are hydrolyzed to volatile acids, glycerol and fatty acids, and amino acids, respectively. It is obvious that in the case of proteins, there is the formation also of some bioproducts, like due to the presence of the amino group in the amino acids, and also of some elements, for example, the sulfurin, cysteine, and methionine. This leads to the formation of amines, ammonia, nitrogen mercaptans, indols, cattle, and hydrogen sulfide. The first stage is the hydrolysis of biopolymers. During this stage, there's an increase in biological oxygen demand as the result of the fact that we have biopolymers which are not biodegradable, are difficultly biodegradable, and after the hydrolysis, they are converted to easily biodegradable monomers. These are the most important hydrolytic populations. There are members of the genus Clostridium, which are the main responsible for their hydrolysis. Some Clostridia are able to prefer proteins as carbon source, other polysaccharides, and other lipids. Obviously, there are also other bacteria that participate to these hydrolysis reactions, but the Clostridia are, without any doubt, the most important ones. It is strange that some of these bacteria are aerobic. What are doing aerobic bacteria within an anaerobic digester? We cannot forget that the sludge to be digested often comes from treatment plants, aerobic treatment plants. Therefore, for example, Bacillus, which is an aerobic bacteria able to form resistant spores, is able to face the stringent anaerobic condition within a digester, and so we are able to detect it at the outlet. The second stage is the fermentation of the organic matter, the organic monomers released by the previous stage, which are transformed to organic acid by the so-called transition bacteria, which are resistant to low pH, obviously, because the acids are the result of their metabolism. The simple sugar are transformed mainly into acetic acid and some other volatile acids. The unsaturated fatty acids present in the lipids are saturated, and these are degraded very, very slowly to low-chain organic acid. The proteins are hydrolyzed to amino acid in the previous step, and then hydroxylated, saturated, and degraded to saturated acid with a lower number of carbon atoms. But this reaction, the last reaction, are very slow. Among the bacteria able to make this fermentation, we are the true fermenting bacteria that convert the organic monomers into acetic, propionic, and butyric acids, but also to ethanol, to hydrogen, CO2. But there are also hydrogen producing acetogenic bacteria and hydrogen consuming acetogenic bacteria. The first class includes some well-known microorganisms, the Clostridium, but also Ximomonas mobilis, which is the microorganism utilized, for example, for alcoholic fermentation to produce tequila. Other reactions are the transformation to acetic acid of amino acid and sugars, which is performed by Clostridia, Bacillus, Streptococcus, Pseudomonas. The fermentation to propionic and butyric acid made by Clostridia, Streptococcus bacterium of sugars and fatty acids, and direct alcohol fermentation and fermentation of fatty acid to CO2 and hydrogen by some bacteria. Very important is the role of the hydrogen-producing acetogenic bacteria, in particular, members of the genera Syntrophomonas and Syntrophobacter. We can give a look at these two reactions. The first one is better. This is the propionic acid, which is transformed by this bacteria to acetic acid and CO2, which here is written as bicarbonate because at pH 7 in the cytoplasm of a cell or in the inside of an aerobic digester, the CO2 is present mainly as bicarbonate. But we can see that this reaction is impossible because of thermodynamic constraints. For example, we have here, we have to remember that this is the, are you seeing the cursor? No.
Yes, we can see.
Okay.
Yeah.
This is the equation that regulates any process. To be spontaneous, a phenomenon must have a reduction of the Gibbs free energy. The Gibbs free energy is given by the value of the Gibbs energy variation under standard biological condition more this term which depends on the equilibrium constant. If we substitute this value of the standard variation of Gibbs free energy here, we can calculate that the delta G would be negative only if the partial pressure of hydrogen would be lower than this value, which is a very, very little value compared to the percentage that I have presented in a previous slide. The percentage of hydrogen in a digester is around 1–2%. So if this metabolism is impossible, how we can detect Synthrophomonas and Synthrophobacter here in our anaerobic digestion? On the reality, the metabolism of these bacteria, which are fundamental to give a link between the first stage and the third one, is only possible if there is another bacterium able to utilize the CO2 and the hydrogen produced by these ones to form methane. In other words, these microorganisms are only able to live in a synergism with methanobacteria, able to remove the products of their metabolism. This was confirmed by the evolution during the last decade of the microscopic tools that identified just a combination of these bacteria in a combination of these bacteria. The methanogenesis perhaps is the most interesting topic of the anaerobic digestion. It is the fermentation to CO2 and methane of simple organic substances. As I have told before, we have two categories of methanobacteria. The ones able to make these, to utilize organic substances to produce methane, but also the autotrophic one able to hydrogenate the CO2 to methane. All them are archaebacteria, which are considered bacteria which kept were not able to evolve in a sufficient way because of they are very similar to this a structure very similar to the one that probably was the structure of the first cells appeared on the earth, because of very drastic condition. They had only very few chances to develop, to evolve, and now have a structure very different from the one of the eubacteria. The optimum pH of the methanobacteria is around 7 in neutrality. After the anaerobic digestion, the sludge has a dark color, is darker than the incoming sludge to be digested, has little smell, high concentration, and reduced volume. These are the two main reactions of the production of methane. The one of the metabolism performed by the acetoclastic bacteria, from acetic acid to methane. The main bacteria of this type belong to the genera Methanosarcina and Methanothrix. We can see that they have a very, very long application time. We can compare this value, 1–3 days, with the application time of Escherichia coli. the most known eubacterium that has, under optimal condition, about half an hour of duplication time. This bacteria are responsible for about 70% of the produced methane, while the remaining 30% is produced by the other hydrogenotrophic bacteria, which are able to reduce the CO2 with hydrogen to produce methane. They are even slower in their metabolism compared to the others, because they are not able to utilize any carbon source. And these are also alternative, less important reaction that some methanobacteria are able to do. The hydrogenation of methanol, of some amines, formic acid, propionic acid, and so on. The main characteristics of these methanobacteria are, from the point of view of classification, they are obligate anaerobic methanogenic archaea that belong phylogenetically to 7 groups and 17 families. I remember you that within a family there are a lot of genera, and within a genus there are a lot of species. Their cell wall is very different from the one of the eubacteria. For example, peptidoglycan, which is the main constituent of cell wall of eubacteria, is absent in this bacteria and is substituted in some of them by an outer protein shell, in others a polypeptide shell similar to peptidoglycan but not exactly the same. Other differences with eubacteria are the lipids, which are not constituted by a double layer of esters of acetic acid, of fatty acid, but are glycol ethers of hyperenoidic hydrocarbons. In other words, they are similar to the plastic. And even the ribosome are different. There is 2 information. Therefore, we can synthesize it in these slides. We can see here how a hydrogenotrophic bacterium is able to produce methane starting from CO2. We can see that this bacteria, in addition to the previous differences with eubacteria, also have different coenzymes. For example, methanofuran, metharopterin, coenzyme M, which are unknown in the eubacteria. One molecule of CO2 is initially reduced to the formyl group, an aldehydic group linked to the methanofuran. Therefore, it is transferred to the methanopterin. The CO2 is removed, and the methyl group linked to methanopterin is transferred to a coenzyme A, similar to the coenzyme A, and then there is the reduction of the methyl group to methane. While in the synthetic route on the bottom, we can see how another molecule of CO2 is able to be transformed into acetyl coenzyme A, which is the main building block that a cell can use to produce cell material. There is the intervention of a specific enzyme, the carbon monoxide dehydrogenase, that receive the methyl, a portion of the methyl group linked to methanopterin to to make this transformation. And this is the equivalent metabolic route of the acetoclastic bacteria, the heterotrophic ones. In some aspect, it appears to be almost the reverse of the metabolism of the other. The acetic acid is linked to coenzyme A to produce the acetyl coenzyme A, which is partly addressed to the biosynthetic routes for cell growth, etc., and partly is subjected to the carbon monoxide dehydrogenase activity. The methyl group is transferred to the corinoid proteins, like in the previous case. And finally, we have the formation of methane. The last step, this one, releases a sufficient energy to phosphorylate one molecule of adenosine diphosphate to adenosine triphosphate, which is the money of energy within a cell. We can see the complexity of the classification of methanobacteria. We can see here in a biodigester that there are 7 different groups, each one including more than one genus. We can meet all the known morphologies for bacteria, Rhodes, Golgi, Spirilla, Dishes, etc., Sarsinus. And these are the substrate. We can see that some of them are able to utilize organic substances, or the others only CO2 as a carbon source. In this table, we can see that almost all the methanobacteria prefer the mesophilic range of temperature between 30 and 40 degrees, except one, this one, Methanobacterium thermoautotrophicum, that is a thermophilic methanobacterium with optimal temperature around 65-70 degrees, and all of them prefer neutral condition, with only this exception, the one of Methanococcus vanielli, that that prefers slightly alkaline conditions. The result is that in an aerobic digestion, we have to control, especially the pH and the temperature, respectively to neutral conditions and the mesophilic range. But it is very important to control the acidity, because the metabolism of methanobacteria is much slower than that of the transition bacteria. Therefore, if we manage a digester with a too high organic load, the risk is an imbalance towards the acidogenic phase, because the methanobacteria are not able to transform the acetic acid sufficiently rapidly to methane. For this, we can control the acidity, or as a total tritratable acidity, as expressed as calcium carbonate, whose maximum value should not exceed 4,000 ppm, or gas chromatographically as expressed as acetic acid with a maximum of 200 ppm. It is also important to control the nitrogen-carbon ratio, which must be, being this one a biological process, very close to the elemental composition of any biological material. This is the less sophisticated configuration, the low-load digester, which is lacking either of mixing or the temperature control. For this reason we must utilize a very low load to avoid the imbalance. These are some information about this low load digester. They are very, very large, maximum 8 of 20 meters, which is only the 8 that we are able to see, because the remaining portion is underground. And the maximum width can reach even 50 meters. No mixing and no heating. This is a medium load digester where we have a system for the mixing guaranteed by recirculation of the digesting sludge, which is transferred into a boiler where there is the control of temperature. The problem of this scheme is that sometimes it is absolutely necessary to stop the recirculation of sludge to let the digested sludge to settle, which can be this problem can be solved in the high load digester scheme, where we have 2 digesters. The former is responsible for about 2/3 of the biogas produced. The second one, the latter, acts especially as a settler and complete, obviously, the anaerobic digestion of the former. Theoretically, it may be sufficient volume of the latter, which is about 1/2 of the former. But if we buy 2 digesters, if they have exactly the same volume, the cost is much lower than if we buy 2 digesters of different cost. For this reason, generally it is used a digester of the same volume, also to have the possibility to exploit the additional volume as a reservoir, for example. In this configuration, we have mixing, heating, and the settling of the digested sludge. What we have done in Genoa is the attempt to transform the biogas into biomethane for some for some obvious reasons. The price. The natural gas is a price that varies from 0.1 up to $0.5 per cubic meter, and the biogas almost the same. The problem is that the methane has a value of some order of magnitude higher. Therefore, the interest to produce biomethane, eliminating the CO2 contained in the biogas. We can see that the density of the air is 2.9 kilograms per normal cubic meter, but that of all them, the natural gas, biogas, and methane are very lower. Therefore, the necessity to recover the methane to produce energy. This is the scheme that we have utilized in our laboratory to make the digestion here and to it is unstable, the internet. Are you able to listen me?
We are, yeah.
Okay, perfect. We have transferred it into a closed photobioreactor, and the feeding material was mixed sludge from sewage treatment. The photobioreactor was very little, 1 liter the temperature was in the mesophilic range, 30 degrees, the pH higher than the neutrality, because the microalgae, in this case, we have used the Cyanobacterium, Arthrospira platensis, prefer alkaline conditions. And these are the most important results. We have obtained a yield of biogas referred to the entering COD of about 0.4 cubic meter per kilograms of COD. The yield of methane was 0.3 cubic meter per kilogram COD. And the percentage of methane increased up to 75%, while that of CO2 decreased to 15%. Interesting is this graph on the bottom, where we can see that practically all the CO2 contained in the biogas was transformed into biomass, in microalgae biomass. And this is another scheme utilized in the same laboratory, where we have used as feeding material olive pomace pretreated by organosolv. The photobioreactor was different, a glass column with mixing. The temperature was lower because we have used an eukaryotic organism, a microalgae, Chlorella vulgaris, that prefer lower temperatures. And we have used a stirring tank digester, regulated at in the mesophilic range and obviously under neutral conditions. Stripping of CO2 produced by photosynthesis, by quick biogas fluxing. One of the problems of this transformation of biogas into biomethane is that the photoautotrophic metabolism of microalgae leads not only to the production, to the removal of CO2, but also to production of oxygen. And this may be a problem to be solved at industrial level, because the mixture oxygen methane poses problems of health, of security. These are the results obtained for this the second configuration, which can be summarized here. The CO2 utilization efficiency for biomass production was 95%. And these are the results of the analysis done on the biomass of microalgae, which revealed the composition in terms of for example, saturated fatty acid, monounsaturated fatty acid, and polyunsaturated fatty acid, not so good for the production of biofuels, but rather to produce a mixture of interest for the food industry. Thank you very much for your attention.
Thank you so much, Professor Converti. I always enjoy your lectures, and I remember that I passed this course with you in 2004, so almost 20 years ago. It was great, refreshing my mind. Thank you so much. Is there any question from the audience? There is one in here that asking about, have you considered the possibility of upgrading biogas to biomethane using macroalgae? That I think you answered in your last slides, but can you summarize that again?
We have tried to exploit the autotrophic metabolism either of cyanobacteria or of eukaryotic microalgae like Chlorella vulgaris to completely, almost completely remove the CO2, and the main products are methane, biomass, because the microorganisms utilize the CO2 to grow. The problem is the production of oxygen that at the larger scale may be a problem. Therefore, this line of research is parallel to the one presented by Professor Casazza, because the laboratory is the same. Therefore, it is an additional topic in the same line.
Mm-hmm. Great. Thank you so much. Any other questions? If no, thank you so much again, Professor Converti, for taking the time on your Sunday evening. We really appreciate your time.
It is a pleasure for me.
Thank you so much. Okay, we can move to our next speaker, Dr. Paolo Truccillo. He is a chemical engineer with a PhD in industrial engineering. He is currently researcher at the Federico II University of Naples in Italy. He has expertise in supercritical fluids for the production of liposomes, extraction of valuable metals from spent catalysts, recovery of dye from wastewaters of the textile industries, biomass pyrolysis and copyrolysis aimed at the production of bio-oils for fuels. Thank you so much, Paolo, Dr. Truccillo, to joining us. And when you are ready, Professor Converti, if you can stop sharing, then
oh yeah.
Thank you so much.
Just a moment.
Sure, we have time.
In the meanwhile, thank you for your presentation. I'm very glad to be here, to be invited by you to take part to this conference.
Thank you.
So shall I?
Yeah, you can start, please.
Okay. Okay, so today I will talk about sustainability indicators evaluation for the development of greener processes. We will start from the problem. So the problem of low sustainability of several manufacturing processes. I will give a sort of proposal in order to take into account simultaneously of profit, social impact, and environmental impact of a process. So in order to evaluate a process under different aspects of views, and I will give a very simple method that could be complementary to life cycle assessment analysis. And then I will conclude by making some examples of low sustainable processes compared with more sustainable processes in similar environments and fields of application. So we know where are we going. We don't know if we know exactly, since we are constantly asked to balance what is green by what is gray in our world. And now we are facing a lot of differences among the population in our earth among countries, especially for the different distribution of resources of our earth. So we have to say that life on Earth, now we know this problem very well, is not balanced. There are many causes that we have been heard for a long time, like the population increase in some areas, in some regions, geographical regions of the Earth, an unequal distribution of wealth, uncontrolled industrial production, and uncontrolled waste disposal. So something changed over years. So yesterday we were using plastics. Now the problem of plastics is a very common problem. Everyone knows about those problems. We have talked about microplastics that are also inside us, unfortunately. And today we are trying to face those problems with the elimination of plastic as much as possible from the processes. However, there are something that has not changed at all between yesterday and today. Today, we should need 1.7 Earth resources in order to balance the speed with which we are consuming them and the speed with which they are regenerated by the Earth. So in order to get a zero net velocity, we should need 1.7 Earth resources. So this is not good, of course. Maybe this is caused by the use of linear economy. That is a concept that is radicated inside us. We just start from raw materials. We make production, so we transform raw materials into final product. Then we distribute products. Consumption is the successive step, the following step. And finally, after using something, we have the waste that is just thrown away. We tried to divide, to separate, to reuse in some cases those objects, but not always this linear economy concept was successful. That's why we tried to introduce the very known concept of circular economy in order to talk about sustainability. So we started talking about sustainability, trying to eliminate the waste word from our speech, from our daily life. So we try to start from raw materials, we made the transformation, we produce, distribute, make the consumption, use, then we can collect, separate the components of those objects, try to collect them, and then try to reuse and recycle those materials in order to make new products in a circular manner, in a cyclic manner. In this manner, the residual waste is quite negligible, and this is the aim that we should have nowadays. So humans have developed a lot of processes to improve the industrial production, because the request of, for example, mobile phones or microchips, for example, it has increased exponentially. However, we have to evaluate our processes in order to improve them. Okay, but it is not just a matter of carbon dioxide emission, not just a matter of life cycle assessment analysis. It is not sufficient anymore to use mass and energy balances and to talk about waste management. We have to do more, in my opinion. So there are several ways, as I said, and aspects that we can use to measure sustainability, and profit is not sufficient to define a process. We have to take care about the environmental impact, but also the social impact. How can we measure sustainability? We have to use our resources in order to satisfy the human needs, of course, but we don't have to compromise the future availability of resources. So what we were saying about the Earth resources, that we need 1.7 Earth resources in order to balance the velocity of consumption and regeneration. In this manner, when we reach zero net speed of consumption and minus regeneration, we are talking about sustainable consumption and development. However, in order to have a sustainable development, we have to intersect simultaneously social, economic, and environmental impact. So we will have an intersection among environmental and social that will be bearable. It will be viable, the intersection among environment and economic, and equitable, the intersection among social and economic. So if we manage to simultaneously intersect the three, we can have finally a process that can be defined sustainable. So we are not just talking about carbon dioxide emissions. If we can maximize the profit reduce as much as possible consumption of resources and energy, environmental impact and social impact. So also we are talking about the bias related to a process. The social impact could be something like that. In this manner, we will have a sustainable process. How can we evaluate a process? Under different point of views. So we can acquire information about raw material mass, the number or the mass of toxic materials, the percentage of material that we can recycle in our process, the consumption of energy of each unit process that we use in our process steps, the number of operators, but also injuries, the hours of training of operators related to injuries, the equivalent CO2, of course, per kilograms of production, investment costs, and return on investment. Those are just a little amount of things that we can acquire if we analyze a process. Then what can we do? We can build ad hoc indicators, so specifically for complementary analysis. So analysis that will be complementary to the classic life cycle assessment. So there should be the mass of hazardous materials over mass of products, the energy required over mass of products, or the energy required over revenues obtained, and so on, up to the for example, number of fatalities over hours of prevention. So we can correlate those information very easily with a criteria that we can define by describing our process. But then the question is how to compare them, because we have a kilograms over kilograms, kilojoule over kilogram, kilojoule over euros or dollars, cubic meter over kilograms, or maybe dimensionless numbers. So how can we compare hamburgers with apples? Of course, there is a simple way to calculate and to make those values dimensionless in order to calculate a score in terms of percentage. So imagine to have this simple formula that compares your actual value, that is your working process today, with worst and best conditions. Okay, so on the numerator, you have a difference among your value and the worst condition value. On the denominator, there is a difference among best condition and the worst one. So in this manner, we will have a dimensionless number in which the best value is the best sustainable condition and the worst value is related to the worst sustainable condition process. So with this simple, very simple calculation, we can compare cost with mass, carbon dioxide emission with sales revenues, number of injuries with global warming potential. In other words, we can compare potatoes with onions. How can we define the worst and the best cases? Of course, we can start from the literature. So we go on Google Scholar, just to make a simple example, and we can compare our process with all the process in the world related to that field. Or we can compare our process with a specific manufacturing field. Then we can close as much as possible the range of data if we want to compare our factory with itself. So we can compare, for example, one specific indicator this year with the other years. So in this manner, the best condition will be the year where I got the best mark, and the worst condition, of course, will be the year with the worst mark. Just to make a very simple and funny example, we can represent our process with several lines of production. So let's imagine a farm producing kiwi, blueberry, bananas, apples, and what else. And imagine that this fruit is each kind of fruit is on each vertex. Okay, so let's imagine one indicator is on one vertex. And we can represent our indicators related to our process by using these spider or radar diagrams. Each score that I remember to you is a percentage score, can be defined in these radar diagrams very easily. And I will define an objective function that is the area under this polygon. Okay, so what can we do? we can maximize the objective function as much as possible. That means maximizing the area inside this polygon. So imagine that we are just analyzing our process with before. So this means that should be the gray, sorry, is one of the blue line, the blue polygon, and then we propose some upgrades, some optimization on our process, and the indicators will change, of course. We can propose two different solutions, solution 1 and solution 2, and then we will choose the gray or the orange one that maximize the area simultaneously. Let's make a simple example of process in terms of sustainability. Let's say the process for the production of energy. Just in terms of carbon dioxide emissions per kilowatt hour produced, we can compare the values of very different processes in order to produce energy. And then we will use as best condition the one that has the lowest emissions of carbon dioxide. And the worst one will be in this case, for example, the coal technology for the production of energy. And we will not fix, but set the numbers of best and worst in a calculation of the scores for our process. Then we have to take care not only about carbon dioxide emissions, but about the cost of production, the efficiency of the process, the water used per unit power generated, but also the bias, so the social impact of having this kind of plant generation nearby my home, the investment cost, and safety fatalities per terawatt hour produced. So in this manner, we can compare in couples, for example, or in triples, the processes for energy production, and we can easily see what is the polygon that wins over the other. Then we can compare everything on the same spider diagram and compare also the average score obtained by working with sustainability indicators. Let's talk about some examples of conventional processes. For example, the essential oil extraction has been made by maceration or percolation. It is easy because we have a solvent that is put in contact with a natural matter. We are going to solubilize the essential oils or active molecules that are inside the vacuoles of the natural matter. This process, however, is characterized by a partial extraction. Sometimes it is necessary, long contact times are necessary in order to saturate the extra-to-rich saturation, and sometimes degradation of active principles occurs. Another not sustainable process, in my opinion, is the extraction of precious metals with the pyrometallurgical or hydrometallurgical methods. In the first case, and we have plenty of examples in many countries, there are very huge areas in which those waste electric and electronic equipments are accumulated every year, and people working with the pyrometallurgical methods without a specific safety condition are there. And hydrometallurgical methods is also not sustainable because it involves, in the first case, high temperatures are required. In second case, the use of acids like aqua regia, for example, nitric acid or hydrochloric acid are used in order to extract those precious metals, but a lot of energy, but also reactive volume is required in order to collect parts per million of those precious metals. Another possibility is the dye recovery from tanning process. We have studied the way the tanning process, in particular the deposition of dye on leather, is performed by using the traditional tanning process. However, not all the dye is able to be put on the ladder. That's why a high percentage of this dye is eliminated in wastewaters. We have studied a way to collect through the adsorption on granular activated carbons and polyurethane foams in order to recover this dye and to reuse it. However, this process is not particularly sustainable. Drug carriers production, another example, the use of drug carriers is usually employed in pharmaceutical but also nutraceutical fields, because drug carriers can protect transport molecules in order to improve their bioavailability and reduce side effects. The use of drug carriers gives the possibility to tune the concentration of drug inside the therapeutic range. This means that we are using a drug that is not in the subtherapeutic range and does not go to the toxic range. In this manner, it is different from the native the free drug administration that gives a very fast concentration of drug, causing side effects, and then in a very few moments I need another administration step in order to provide a sort of efficacy. Instead, with drug carriers we can have one single release with a significant control of drug concentration. However, those processes are characterized by micrometric dimensions, batch layouts, so low reproducibility. So we have the problem generally of solvent residue and post-processing cost. Finally, for the not sustainable processes, we have, for example, crypto values. So this is not drug carrier production, sorry, but the extraction of Bitcoin. Imagine those mining factories that have been built in some places of our country. One of the indicators that we could calculate is the energy consumption over the value of Bitcoin. So imagine that we are consuming a lot of energy that, compared to the value of this kind of money, sometimes could give negative profits. So let's think about this. So in a comparison manner, sustainable processes could be the production of foams for pharmaceutical applications. So imagine now I'm working on disc production with high pressure processes using supercritical carbon dioxide. I'm creating foams, and this means soft matter starting from discs in order to obtain this matter with a very low density, an expansion ratio of more than 600%, and an internal hole structure in order to provide a controlled drug release with a tunable internal structure from nanometric to micrometric, and provide antioxidant activity. In order to remember what I did in my previous experience at the University of Salerno, I was involved in the production of a process for the deposition of dye on leather with an innovative method. We managed to use liposomes in a certain manner, drug carriers for death leather, in order to make the deposition of dye in half time than the conventional method. And finally, the dye was resisted also to water at 100 degrees centigrade and oven at 120 degrees centigrade. Another possibility to extract precious metals instead of using high temperatures or acids is a compact machinery for the extraction of copper. Copper became particularly important in terms of its economic value, but also supply risk after COVID period. Just by using this kind of all-in-one machinery, you can start from the wires, the spent wires, and then you can collect after this all-in-one process just the pellets of copper. Drug carriers production. When I was at University of Salerno, I worked with a process that I working at high pressure temperature with carbon dioxide for the production of lipidic vesicles of nanometric dimensions with encapsulation efficiencies up to 99%. So we disposed very little amount of drug. And we also made a sustainability analysis of this process by introducing a recirculation. Recycled material fraction was having a mark of 0%, and after recirculation we managed to increase it to 40% score, and this increased a lot of other indicators like global warming potential, the liquid waste volume, reaction mass efficiency. In this manner, we managed to increase the sustainability of the process by maximizing this objective function. To conclude my talk, there are some alternative extraction methods. The very well-known supercritical fluids method that is more efficient, but it has higher cost and sometimes is partially versatile. And also with a mild pressure condition and without the use of carbon dioxide, but just ethanol or water, there is the Naviglio extractor that is a sort of a rapid solid liquid extraction that gives the possibility to obtain mandarin and limoncello liquor in just 2 hours that has the same taste and properties and antioxidant activity like the one prepared in 20 days in our homes. You can also make broccoli cooking, but also the wine oldening is a process versatile, efficient, and fast that brings to the saturation natural matter in just 2 hours in case of limoncello, for example, that is a very famous liquor in our region in the south of Italy, and with very low extraction times, as I said. Can we do more than sustainability? Oh, yes. Because with sustainability, we can just bring to zero the net velocity among consumption and regeneration. But we can do more. We can increase the speed of regeneration by developing new processes that can reduce the speed of consumption of resources and increase the one of regenerability. And one example is the ozone regeneration that was significantly damaged by the end of 80s and 90s, and that now, without the use of CFC, we managed to restore. And it will be, it is a regenerative process that will be concluded by 2054, according to our simulations. So I want to thank you for your kind attention, and I want to thank my previous institution that was the University of Salerno on the first line, and now the institution of University of Naples Federico II, where now I'm working. Thank you very much.
Great. Thank you so much, Dr. Truccillo. It was very helpful. Any questions from the audience?
I'm sorry, but my video, but the light,
Yeah.
the light when I was talking, the sunset occurred. So, so now I cannot switch on the light.
Yeah. So we have one question on Huwa. Oh, there is one. Can you talk about circularity and diseases?
What do you mean? So the relationship about the circular economy and diseases? You mean this? If there is a relationship, a correlation, I don't know. So
yes, yes, like yeah. Because with circularity, you could potentially upcycle pathogenic bacteria into the system.
Okay. Of course, when we make the evaluation of a process, we need to take into consideration different kind of sustainability indicators. So I will guess that we need 2 indicators about environmental impact, at least 2 about profit, at least 2 about social impact. So we have to try to define the process under different conditions, under different point of view. So the introduction of a circular way of conceiving the processes should be defined also in terms of indicators. So if I want to avoid that the introduction of a circular path causes some damages, some other kind of damages, I have to take care about this. So I have to build a specific indicator that is maybe related to this possibility. So I have to take into account the possible introduction of damages by changing the path of my process. I don't know if I answered to your question.
Yes, thank you.
Yeah, well.
Thank you. And there is one more question about the vertical farm, and they're asking, is vertical farm sustainable farm?
Yeah, I saw this question before. The fact is that if we go vertical, this means that we are going specifically in a kind of in a field of process, right? So we need very specific definition of indicators. So I will guess that if my customer ask me to define, certify the sustainability of his farm, I would ask him or her all the information about the production, all the information about waste production and disposal, and all information about each line of production. In this manner, I can be very vertical in this direction, but I have to also to define specific indicators in order to answer to his or her question.
Mm-hmm. Great. Thank you so much. I'm not seeing any other questions. So thank you so much again, Dr. Truccillo, for your great presentation and for taking the time to join us today. Thank you.
Thank you very much.
Okay, now we can move to our other presentations, which are focused on the food waste and food waste valorization. We have our next speaker, Dr. Margherita Pettinato. She is currently an assistant professor at the University of Genoa, Department of Civil, Chemical, and Environmental Engineering. Her main research topics concern the recovery of high added value components by the valorization of agri-food industry byproducts using non-conventional extraction techniques. She also worked with the preservation of their bioactivity and bioavailability by macro and nano encapsulation processes and the application of added value components in active food packaging. Dr. Pettinato's research activity resulted in several publications in international journals and are presented at national and international conferences. Thank you so much for joining us today, Dr. Pettinato, and now the floor is yours.
Thank you, Dr. Alekbarian, for the kind introduction and for the invitation. I try to share the screen on my presentation. Please let me know if the presentation is correctly shared.
Yes, it is. Perfect.
Okay. So in this presentation, I would like to share with you the path that led our research group to the invention, implementation, and design of a new extraction technology titled SOLV, which stands for Solid Liquid Multivariable Extractor. The development of this new technique is related to one of the main topics which are covered by our research group concerning the valorization of byproducts coming from the agri-food industry sector. Indeed, currently is recognized at international level that the management of agri-food industry wastes is a problem that needs a solution. Indeed, the Food and Agriculture Organization estimated that yearly about 1.6 billion tons of waste are produced by this sector, of which about 1.3 billion tons are associated to food wastage. In particular, the industry treating fruits and vegetables is responsible of one of the greatest impact in terms of volume of wastes. It must be noted that only a small percentage of such byproducts are treated, for example, by composting, while the remaining part is disposed by landfilling, generating a great amount of greenhouse gases emission due to the high organic matter related to this kind of byproducts. In addition, especially vegetable-derived waste, are rich in phenolic compounds, which can contribute to the soil and water pollution. Indeed, if released and accumulated in the soil, these compounds can be phytotoxic by inhibiting the plant growth, but at the same time, they can exert also antimicrobial activity, so they can damage the strains which are essential to ensure the health of the soil. Moreover, by percolation, this compound can also reach the water environment, resulting as toxic for aquatic organisms. But the same compounds often show some properties that can be used in several fields of the industries. Indeed, for example, phenolic compounds or carotenoids are antioxidants, so they are able to counteract the oxidative stress in our body, so preventing development of aging and of other chronic diseases such as cardiovascular pathologies and cancer. So phenolic compounds like chlorogenic acid or caffeic acid or carotenoids can be recovered from byproducts like wastes of the coffee industry, of tomato skins, to be used as natural antioxidants in the food, cosmetic and pharmaceutical sectors. In addition, these compounds, these bioactive compounds, can also respond to the growing demand of the market of natural derived components to replace synthetic ones. This is motivated by the increasing awareness of consumers towards a healthier lifestyle. In addition, the antioxidant, anti-inflammatory, antiviral properties exhibited by some of the compounds that can be recovered from agri-food industry byproduct can help, for example, in improving the life quality of older people, so reducing the healthcare costs, and can also help to facing with emerging hazards, such as the diffusion of new diseases. Another example of a potential application in the food industry is, for example, the use of lycopene, chlorophyll, and anthocyanins that can be recovered from agri-food waste as natural pigments to replace synthetic food colorants. Indeed, to the latter, some concerns are related to some side effects they can have, for example, allergic reaction or a short-term or long-term toxicity. Instead, naturally derived food colorants do not show any side effect and instead can improve human health. It's worthy to mention, in addition, that to approach the zero waste concept is theoretically possible, starting from a single biomass, to valorize the waste by using solution applied according to logic hierarchy, in order, for example, to firstly recover the high added value compounds that can be used in the pharmaceutical, food, and cosmetic industry, and to continue to valorize the residue of the first extraction for the recovery of other compounds of interest for the industry up to the final exploitation, for example, for energy recovery, according to the concept of a biorefinery. But the first step of this biorefinery, considering the intended use of the product we want to recover from waste, must comply with the principle of green chemistry, which imply the design and application of chemical products and processes to reduce or to eliminate the use and generation of hazardous substances. When referred to extraction processes, this definition implies also the discovery and design of extraction processes which will reduce energy consumption, allows the use of alternative solvents and renewable natural products, and ensure a safe and high quality product. This definition was summarized by Shema and co-workers in 6 principles, which sometimes match with the principle of inherent safety design. The last is an approach used in the design of chemical processes, which aims to reduce the hazards and the probabilities of errors, as well as consequences of accident, by measures that must be applied at the early stage of design of processes. But the main challenge, if you want to comply with the principle of green chemistry, is mainly related to the requirement of using solvents that are generally considered as safe. Indeed, this kind of solvents can potentially be less suitable for the efficient extraction of the target compound. But this issue can be overcome by introducing new extraction aids and working on the operating condition to perform an optimization. On the other hand, we have to remember that most of the compounds we want to recover are thermosensitive. So pushing too much on the variables that are able to increase the mass transfer, such as temperature, can have the undesired effect of providing degradation of the activity of the bioactive compounds. So it's necessary a careful optimization of the process to obtain high extraction yields, but also to prevent the losses of bioactivity. Another challenge when we talk about processes in which the raw material are the agri-food industry byproduct is the variation in the composition and in the amount of the raw material. This implies the need to design flexible processes able to absorb the oscillation in the variation in the feed, providing products with variation, but within acceptable limits. In this context, our research team planned to design a new extraction technology in which a lot of extraction aids are available and the operating condition can be tuned ad hoc in order to process different kind of biomasses and to recover molecules with different properties. The technology, titled SOLVE, was patented by our research group, and the development of the prototype was funded by the Italian Ministry of Economic Development under a proof of concept project which aimed to the valorization of university patents. In this slide, you can see a potential configuration of SOLVE, which consists of a mixing system of 2 or more solvents, which are then pressurized and sent to the packet bed extraction columns. Here, strict control of temperature is performed. Indeed, the temperature of the solvent, of the extraction chambers, and of the extract can be increased or decreased as a function of the thermosensitivity of the compounds to be treated. Pressure can play a pivotal role in enhancing the extraction process, but in this device, it has also a second function. Indeed, it is also the driving force for the simultaneous separation of the solid residue from the extract. This separation is obtained by filtration thanks to micrometric filters, which are located in the outlet sections of the extraction chambers. In addition, ultrasounds are applied on the extraction chambers in order to increase the efficiency of the extraction process, especially when thermosensitive compounds must be treated. Indeed, thanks to the cavitation phenomenon, the ultrasounds generated by a probe are able to increase the extraction efficiency and the release of the compounds by matrix disruption and micromixing of the packed bed. By the ultrasound, it's then possible to achieve high extraction yields in shorter time and by exploiting lower amounts of solvents. So this technique aims to combine the positive effects of ultrasound-assisted extraction and pressurized liquid extraction, but making available, in addition, a large number of extraction parameters to be tuned in order to obtain an ad hoc solution for different kinds of biomasses and compounds. To validate the idea behind the technology, the extraction method was tested on several biomasses with different characteristics and to recover different molecules and compounds with different properties. The first one was spent coffee grounds, a matrix that was widely studied by our research group in the past, and on which several extraction techniques were used to recover polyphenols from conventional solid liquid extraction to microwave and high pressure and temperature assisted extraction. From these previous studies, we noticed that effectively these extraction aids are able to increase the extraction performances, for example, as can be observed in the slide for the total polyphenol yields. But to test the effectiveness of the proposed technology on the recovery of bioactive molecules from spent coffee grounds, an experimental plan was elaborated in order to investigate the effect of two input variables, particularly the solvent composition and the ultrasound amplitude, on the extraction performances. In particular, 3 different solvent combinations were used and coded into 3 different levels. At the level -1 corresponded the use of ethanol 54% as solvent, while at the level 0 only pure water was used as solvent, while at the level +1 the extraction was carried out by fluxing ethanol 54% for a time equal to the half of the total extraction time, and by fluxing water for the remainder part of the time. The other input variable analyzed was the ultrasound amplitude, which was varied between 20 and 80%. The effects of the 2 parameters were analyzed on the total polyphenol content, the anti-radical power of the extract, as well as on the caffeine and chlorogenic acid content. In the slide is reported the experimental plan given by the combination of the 2 input variables with 11 runs randomly organized, and also the values of the response variables obtained is reported. But summarizing the results, it was observed that the total polyphenol content was maximized when the composition of the solvent was changed during the extraction process. Indeed, at the level +1 corresponding to the change of the solvent composition from ethanol 54% to water corresponded the highest amount of total polyphenols extracted. A similar behavior was observed for chlorogenic acid extraction. Indeed, the highest yields were obtained again when the solvent composition was changed. Similarly, was obtained also for caffeine. Indeed, even in this case, the lower was the amplitude of the ultrasound applied, the highest was the extraction yield, especially when the solvent composition was changed from ethanol 54% to water during the extraction time. But not only the amount of extracted compound was increased by this possibility offered by this technology, but also the quality of the extract in terms of anti-radical power. Indeed, even in this case, it was maximized when the solvent composition was changed over time. So the positive results obtained from spent coffee grounds enable the possibility to explore also different biomasses. So in a second case study, we analyzed the possibility to recover two different classes of compounds, the hydrophilic polyphenols and the hydrophobic lycopene from tomato skins coming from the tomato sauce production process. To investigate the possibility, another factorial plan was elaborated, but analyzing as input variable the pressure, the temperature, and the solvent composition, which was composed of a solution of ethanol and water. To analyze the effect of this variable, first of all, it was analyzed the kinetic of the extraction by adopting the Peleg's model and obtaining the kinetic parameter of the model K1 and K2, and then the dependencies of these two parameters from the input variables was used a response surface modeling. So from the experimental test and from the modeling by the Peleg model of the extraction kinetic, the experimental values of K1 and K2, which represents respectively the reciprocal of the initial extraction rate and the reciprocal of the concentration of the target compound at infinite time. So once the experimental value are obtained, the dependence on the input variable was modeled by response surface modeling, which gave us results, the equation reported in the slide, which are depicted in the surface plot, also reported in the slide. From the optimization resulted thus the total polyphenol content in the extract can be maximized by working at 50 bar and at a temperature of 95 Celsius degree and using ethanol 53% as solvent. But under this condition, no lycopene was detected in the solvent. Indeed, from experimental results, we saw that the lycopene extraction can be obtained only when pure ethanol is used as solvent. So the idea is to selectively recover first the polyphenols by fluxing ethanol 53% as solvent and then moving to pure ethanol in order to selectively recover only lycopene. In this way is performed an insidious extraction by recovering two different classes of compounds from the same biomass. This configuration is possible, is allowed by the proposed technology, so the extraction in series is performed in a single device without dead times and with a safe management of solvents. but other variables are available thanks to the proposed technology. Indeed, for example, the effect of temperature, time, liquid to solid ratio, ultrasound amplitude, and ultrasound pulsation ratio can be analyzed, as we did in another study, aimed to maximize the extraction of lycopene from tomato waste. So by using the same approach described before, the dependencies of the initial extraction rate and of the concentration of lycopene at infinite time as a function of the input variable was obtained, and by a numerical optimization, the best values of the operating parameter was obtained. But this technique, albeit is particularly suitable for the recovery of compounds from agri-food waste, can be also used for other purposes, such as the decontamination of polluted solids. So to test this possibility, another case study involved the use of a spent ion exchange resin, which was used in a system for water deionization in order to see if it's possible to regenerate the resin after the use. In this study, we compared the performances of SOV with the conventional solid liquid extraction. And in the graph, you can see is reported the ability of the two extraction technique in the removal of magnesium from the spent resin. It's easy to see as the SOV technique was able to remove a higher amount of magnesium compared to solid liquid extraction in a shorter time. So to validate the idea behind this technology, we started with a lab scale prototype which limited function, but this was gradually implemented, for example, replacing the pump for the solvent pressurization, which was initially able to process only 1 solvent per time, with a more powerful one able to process up to 4 different solvents, so enabling the possibility of verifying the effect of the changing of composition of the solvent over time on the extraction performances. By this second prototype, in addition, we validated also the effects of other parameters, such as the liquid to solid ratio, the effect of the chamber volume, the solvent flow rate, the pressure that can be applied in static, dynamic, and pulsed mode, the temperature in different sections of the plant, and the ultrasound amplitude and pulsation ratio. At the moment, the technology was further implemented, and the technology was validated in the laboratory. And by this last prototype, we are trying to work on a larger scale, which is possible not only thanks to the larger extraction chamber that are used in this last prototype, but also thanks to the modularity of the system. Indeed, we can work simultaneously with different columns, which can work in parallel or alternate manner in order to provide a continuous process even solid side. So at the moment, the system scalability is testing is underway. Moving to the conclusion, the SOV technology represents our effort to contribute to the smart management of agri-food industry byproduct. Of course, it's possible to obtain more sustainable products starting from such kind of raw materials. Of course, there are problems which need some solutions, some technological problems, but this one can be the driving force for technological innovation. It must be noted that when new processes are used, they can, even if they are designed under the principle of this green chemistry, they can potentially introduce new hazards if compared with conventional processes. So the equivalence between green and safe must not be taken for granted. So in the future research, we would like to integrate in the design process not only the green extraction principles, but in addition also the inherent safety design in order to obtain processes and solutions that are not only the least impacted from an environmental point of view, but that are able to guarantee also a higher safety for the consumers and the workers as well. My presentation has ended, and I would like to thank you for the kind attention.
Thank you so much, Dr. Pettinato. It was very interesting. So any question from the audience?
How about the commercialization of this kind of technology so far? I mean, how feasible they are to be commercialized?
Okay.
He's asking about the feasibility for commercialization and
Yeah.
scaling up. Yeah.
Thank you for the question. Okay, at the moment we are validating the technology, and we are in contact with some companies which are interested in the patent. Our idea when we developed this kind of process was double. Indeed, of course, this technology is particularly suitable for the research, since a lot of variables can be analyzed. And I'm talking about both academic research and industrial research. So one of the aims is to commercialize this technology as a laboratory technology aimed to research. And of course, if there are processes which are particularly suitable for this technology, the scalability to an industrial scale can be evaluated, and also the technology can be commercialized at this industrial level.
Thank you. And just a curiosity, have you guys thought about doing any life cycle assessment analysis of the process?
About the salt technology?
Yeah,
No,
about salt technology.
Not at the moment, but it could be really interesting. Above all, to have a comparison between among several non-conventional extraction techniques to see if effectively this can be a solution more sustainable than others.
Yep, great. Okay. Again, thank you so much for taking the time. It was very good presentation. Thank you again.
Thank you for your time.
Okay. And our next speaker, last but not least, is Dr. Pierfrancesco Ferrari. He is a researcher at the Department of Civil, Chemical, and Environmental Engineering at the University of Genoa. He is carrying out multidisciplinary studies aimed to investigate engineered devices for personalized and precision medicine. He has experience in biomaterials for regenerative medicine and vascular tissue engineering, bioreactors for scaffold validation studies, nanotechnology with the diagnostic approach, and innovative biosensors for protein detection in biological fluids. Thank you so much for joining us today, and please share your screen.
Okay, so I'm sharing the screen. Okay.
Perfect. Thank you.
So, good afternoon, everyone. I would like at first to thank Professor Bahar Aliakbaryan for the introduction. Today, I will share with you some key points on how food waste could be transformed in bioengineeristic tools. In general, biomaterials, food packaging, and drug delivery systems. So, considering the actual increase of the world population, it is necessary to take into account the total global consumption of food that is directly related to the food waste production and consequently to the food waste management. Wastes from food are considered really dangerous for the environment because of their plenty of organic compounds, such as lipids, carbohydrates, proteins, nucleic acids, and of course, also secondary metabolites. Food waste can indeed act as pollutants if they are not disposed of properly. When food waste ends up in landfills, it decomposes and could produce, for example, methane gas, a potent greenhouse gas that contributes negatively to climate change. So, in order to reduce the negative environmental impact of food waste, it is important, of course, to reduce the amount of food waste generated, but also to find new strategies. And the new strategies are focused on the removal of these organic compounds. Some of these molecules could be considered high added value compounds because of they possess a positive impact, especially on human and animal health. So the real question is this one. Is it possible to turn a problem into a resource in the field of food waste? The answer is yes, we can. But how is it possible? By the recovery of these compounds that could be used for giving different functionalities. At first to food, for example, transforming it in nutraceuticals, or also to biomaterials, giving rise to active scaffolds, or at least to food packaging, obtaining active food packaging, and of course to cosmetics. The first step of our research is always addressed to the optimization of the extraction parameters of these bioactive compounds from different kinds of food waste. During the last decade, different biomasses were taken into consideration by the research group, such as, for example, spent coffee ground or olive pomace, corn silage, apple skin, and microalgae. Different green extraction techniques that employ, for example, ultrasounds, microwaves, high pressure and high temperature, or the combination of them, were used to obtain extract with high concentration of these high added value compounds. Once the extract has been obtained, it is usually characterized by measuring the high added value compound content. These molecules belong to the group of polyphenols, anthocyanins, and flavonoids, and they are quantified by using specific colorimetric assays. The research group has also tried to give them the correct name by high-performance liquid chromatography analysis. Before becoming a part of a novel food or of a cosmetic, these extracts have been biologically validated by using different cell lineage. So we have used, for example, hepatic cells to understand if they have a role in preventing the hepatic steatosis. We have also used skeletal muscle cells and endothelial cells, focusing on the ability of these molecules to counteract endothelial dysfunction and the related inflammation. We have also studied the effect of this extract on cortical neurons, and in particular on the capability of this extract to prevent the calcium-mediated cytotoxicity. In details, for example, regarding the vascular field, so we have studied the anti-inflammatory properties that these molecules could have, the extract and the single molecules. For example, we have set up an in vitro model in which endothelial cells became inflamed after the treatment with tumor necrosis alpha, that is a pro-inflammatory cytokine. The molecules that are in the extract are able to counteract this in vitro derived inflammation process. And this capability was studied by referring to different endothelial cells markers, like, for example, matrix metalloproteinase or nitric oxidase synthase enzymes. So the obtained results in vitro were so promising that the research group has performed also in vivo experimentation by treating rats with resveratrol, an antioxidant common in wastes from wine production. In details, by infusion of elastase, that is an enzyme able to induce vascular pathology, rats presented a real abnormal aneurysm at a level of the abdominal aorta. Rats were forced to the orally consumption of resveratrol for few weeks, and in the treated animals, the inflammation related to the vascular pathology was drastically reduced. I would like to focus my attention on a molecule that was used by our research group for obtaining different bioengineered based tools, in particular nanoparticles, biomaterials, and membranes for innovative food packaging. So a quercetin-rich extract was obtained by Jonagold apples by employing microwave-assisted extraction technique. And the extract was characterized by high-pressure liquid chromatography. So all the steps that I have mentioned before. Considering that quercetin is prone to be oxidized, the first step was to embed these flavonoids in nanoparticles, in particular into nanoliposomes, or in fibers that were obtained by the electrospinning process. So, quercetin is considered one of the most important flavonoids, but as all this class of molecule is a photosensitive molecule, and it is also oxygen sensitive. So it's really important to protect it. And how is possible to protect it? By encapsulation, in particular in micro and nano capsules. So in general, encapsulation represents the confinement of molecules in a well-defined structure, usually spherical structure, made by a coating agent. It is possible to have solid formulation or liquid formulation, and the choice of the encapsulation techniques depends on the final application that the encapsulated product has to have. For example, if we would like to have a solid particle to give rise, for example, to nutraceutics, we have to use the spray drying process. Or, on the other hand, if we would like to have a liquid formulation, such as for biomedical application, we have to use protocols that are focused on complex conservation to produce, for example, inorganic materials, protocols that are suitable for liposome production or for polymeric nanoparticles. Due to the instability of antioxidants, we have developed a different micro and nanoencapsulation technique, and all these particles were characterized in our laboratories. So, for example, we have used complex coadsorption, so nanoaggregates that in the presence of calcium become calcium carbonate particles, sonication for liposome production, or layer by layer technique, and also the double emulsion method to have polymeric emulsion. All these techniques allowed us to obtain different particles, microparticles, also with the capability to encapsulate whole microorganism, bacteria, or microalgae, polymeric nanoparticle made of polycaprolactone that is FDA approved, or polylactic acid, nanoliposomes, also by using supercritical carbon dioxide in collaboration with the University of Salerno. And calcium carbonate nanoparticles to encapsulate, for example, antioxidants, but also proteins, layered particles that represent the best choice to have a sustained release of the drug over time. So, as the first step, every time we move to the in vitro characterization to the in vivo one. Here you can find, for example, some confocal microscope images in which calcium carbonate nanoparticles are reaching the nucleus of the cells that is represented in blue. On the other hand, by working with polymeric nanoparticles, we are performing in vivo feasibility tests to study how the particles are able to be distributed in the whole body of the mouse once they are injected in the tail. In particular, it is really important to understand if there are bioaccumulation in some specific organs. Taking quercetin as an example, I would like to report, like a case study, the encapsulation of these molecules into liposomes. This work was done in collaboration with Université de Lorraine in France, and like ingredients, we have used rapeseed lecithin and quercetin that were mixed together and then sonicated to obtain quercetin-loaded nanoliposomes. So, under a morphological point of view, these liposomes appears as spherical particles with a mean diameter of 200 nanometers, and there was no statistical difference between the quercetin-loaded nanoliposome and the empty nanoliposome. So the presence of quercetin did not negatively influence the process of liposome production, even in terms of zeta potential, electrophoretic mobility, and of course, as I mentioned before, the dimension. To have a nanoliposome that could be used for the different bioengineered based applications, so for food packaging and for drug delivery and engineering of scaffolds, it is really important to study their stability. We have studied the stability in terms of charge and dimension at different temperature. At 4 degrees, to mimic, for example, the meat and the film that is in close contact with the meat in the fridge. So The next step was to validate this stability of nanoliposome by using environmental temperature, for example, for vegetables and for fruits. And then it was really important to assess the stability at 37 degrees. We have to remember that, for example, the Pfizer vaccine is made of nanoliposomes, so it's really important to have these results, this kind of data when we think about an injectable products. Is really fundamental to understand also the release of quercetin from the nanoparticles. In particular, we have studied at the same 3 temperature how the compound is released, and we have found that increasing the working temperature, that was a higher quercetin percentage that was released. This is a really important point because of, for example, when the nanoliposome reach the final tissue for which they are synthesized, it's really important that the quercetin is released, as it is important that quercetin is released in the film during the storage of meat or of fruits and vegetables. So the next step after the chemical and physical characterization of the nanoliposomes was to study the biocompatibility of these nanoparticles with cells. We have selected the fibroblasts for 2 reasons. One, for biomedical application, because of course you can find fibroblasts in all the tissue of our body. On the other end, we have selected this cell lineage because, for example, for the novel food, for the food of the future, it's really important, this kind of cells. By considering the 3D bioprinted meat, you have that the fibroblasts are bioprinted on scaffold. So it's really important that they can form, for example, the hamburger in a really good environment where the oxidative process are prevented and counteracted by the nanoliposomes, for example. Starting to have a complete view of the drug delivery system, we have to mention another important parameter, the hemocompatibility of the nanoparticles. So the capability of these particles to interact with the blood cells and with the blood proteins. Here, for example, we have put together the nanoliposomes with blood, and we have studied if they were able to induce the red blood cell breakage. And as you can see in the graph, for the highest concentration, unfortunately, there was a rupture of these cells. This parameter is really important because of if you have an injectable product, as you can see here, the nanoliposome flow in the bloodstream until they recognize, for example, an antigen or a protein that is recognized by the antibody that are present on the surface of the nanoliposomes. So the contact between the antigen and the antibodies of which the liposome are engineered induce the uptake of liposomes by the cells. And once the nanoliposomes enter in the cells, they are able to release the drug. So the drug is inside the cells, and there it could exercise all the activities for which it is synthesized. But as we have seen before, nanoliposomes could be crucial to engineer membranes, but also free quercetin could be used for this aim. We extract quercetin by microwave extraction. We put the quercetin into a polymeric solution, and then it was used for the electrospinning process. So by the electrospinning process, you can have or bioactive material scaffolds, in our case, vascular prosthesis, or active food packaging, like films. Taking a look to active biomaterials for vascular tissue engineering, they are made of two different polymers. One is the known polycaprolactone that is hydrophobic and is already approved by the Food and Drug Administration. The other one was synthesized in collaboration with MIT, and it is represented by the polyglycerol sebathate. It comes from the polymerization of two monomers, sebacic acid and glycerols. Contrary to polycaprolactone, it is hydrophilic, so combining the polycaprolactone and the polyglycerol sebaceate together in a ratio 1:1, it is possible to have a material that is suitable to replace obstructed vessels. Why have we choose electrospinning? Because of two main reasons. So because of the process of electrospinning is able to induce the collecting of fibers on a rototranslating collector by inducing the formation of a random scaffold made of different fibers that is really close to the extracellular matrix. These properties could be used for vascular prosthesis because of the colonization of the material, but also for example, scaffold for 3D bioprinted food. So the engineered materials could be obtained, or as we have seen before, by adding the antioxidant, the flavonoids, the high added value compounds directly in the polymeric solution, or by the post-synthesis functionalization, for example, by using the plasma technology that is able to induce a covalent bond between these high added value compounds and the polymer themselves. So one of the problems that we have to face was the high porosity of this material. So the porosity, of course, it's a really important parameter because of is essential to have cellular exchanges. But when it is so high, it is a drawback, especially when we would like to replace vessel with our prosthesis. To do that, so to reduce the porosity of the scaffolds, we have used another high added value compounds that derive from food waste, in particular gelatin from bovine bones. And the prosthesis was directly and completely soaked into a solution of gelatin for 1 hour. Then after the UV exposure, it was created a cross-link between the polymer and the proteins, and we have drastically reduced the porosity of the material. After the production, the fabrication of the material, we have characterized them under different point of view. Morphology studies, so scanning electron microscopy, transmission electron microscopy, and atomic force microscopy, physical-chemical characterization to understand the drug release during time, water and gas permeability studies. Water is essential for vascular prosthesis, while gas permeability studies were really important for innovative food packaging. And also all the mechanical properties were studied. Under a biological point of view, it was performed different experiments of biocompatibility, hemocompatibility, suturability, and wettability. So how the geometrical properties of the scaffold can be modulated by different soaking time in physiological solution. So to reduce the number of animals that are usually used in vivo experimentation, we have developed and really important device that is named high-performing bioreactor. This high-performing bioreactor is made of a peristaltic pump that mimic Earth, so it is able to impart to the samples, to the engineered scaffold, a diastolic and systolic pressure, so a pulsatile behavior. Then it is made of a chamber where 3 different scaffolds could be inserted at the same time, a reservoir where the liquid that passes through the scaffolds is storage, and a dampener that is really important to have contraction of the scaffold. So during the experimentation daily, we have collected some aliquots of the liquid to study, for example, as I mentioned before, the different drug release over time. But we have also studied at the end of the experimentation, the morphological properties, the mechanical tests were performed, and we have done the mathematical modeling. So even in this case, it's possible to add quercetin to the scaffolds, and it is possible to obtain quercetin-loaded vascular prosthesis. Under a morphological point of view, the presence of quercetin and the presence of gelatin did not interfere with the random structure of the fibrous material, and the fibers at the diameter of micrometer. Under a physical-chemical point of view, we have studied for the first step, the degradation properties, and here you can see that the material engineered with gelatin and quercetin together present a really higher degradation rate. It depends on the gelatin and on the quercetin that are released from the material, and not from the fiber deformation. So the quercetin, as I mentioned before, was released, and it was really important because this molecule was able to counteract the inflammation process of endothelial cells once the prosthesis was implanted. Under a mechanical properties point of view, the study of gelatin-coated materials were really strange. So it was different from the polymeric ones. But after having the material in a physiological solution, also the gelatin-coated material present the typical stress-strain curve of all the elastomers. So the gelatin was hydrated again, and the mechanical properties were really close to those of the native artery. The permeability test suggests us that our scaffolds were resistant to really high pressure, even higher than a pressure that is compatible with our body, and the presence of quercetin was able to modulate the wound healing. In particular, we have taken endothelial cells, we have done a scratch, so there was a defect on the well plate, and after patting the release medium from the quercetin engineered scaffolds, after 48 hours, the scratch was completely closed. So we can affirm that our quercetin is able to counteract inflammation and to induce the regeneration of the vessels. Here you can see all the mathematical models that we have performed, and we have verified by experimentation in high-performance bioreactor by using pulsatile pressure and a Newtonian fluid. In particular, it is shown the velocity profile of the fluid inside the wall of the prosthesis. So by taking a final look to active food packaging, even in this case, there were fabricated by electrospinning process. The rheological properties of the spinning solution were studied at the beginning. Here we have used different polymers, in particular polylactic acids, and we have studied the quercetin PLLA ratio. We have obtained a different fiber diameter even at the sub-micrometer scale. And in this case, because of the aim of the work, we have studied the release of quercetin at 4 degrees and 20 degrees, and the temperature and also the quercetin PLLA ratio was not modulating the release of quercetin. Another important point was the study of antimicrobial properties. We have used 2 model microorganisms, Escherichia coli as bacteria and Saccharomyces cerevisiae as yeast. And in the plate where there is the scaffold, you can see that the colony forming unit in number are lower than in the control ones. So, in conclusion, by starting from an apple waste, the apple skin, it is possible to extract an high added value compound, quercetin, that is the key character, the protagonist of drug delivery system, because of it is encapsulated in nanoliposomes, or it could be embedded in the fibers of vascular prosthesis for vascular tissue engineering, modulating the inflammation process and guiding the regeneration process, and also in active food packaging with antimicrobial properties and with a really good release of this antioxidant to prevent the pro-oxidative environment of foods. Thank you all for your attention.
Thank you so much, Dr. Ferrari, for this complete and comprehensive study and showcase. Thank you. Any question from the audience? Okay. So thank you so much. Oh, we have, well, just a thank you note from Angie for you.
Thank you.
Wonderful. Okay. So to wrap up this session, as we come to the end of this session, I would like to express my sincere gratitude to our 5 distinguished speakers for sharing their knowledge and expertise on the critical issue of environmental pollution. And I would like to thank these GARD organizers, Dr. Vanji Alosilja and Chelsea. From the wastewater treatment to biogas generation to replace fossil fuels to the importance of sustainability in agriculture and the role of circular economy in reducing waste, we have gained valuable insights in the challenges we face and the actions we can take to address them. It's clear that the issue of environmental pollution requires urgent attention, and the contributions of these experts from across Europe have shown us that we have the tools, knowledge, and expertise to tackle this issue. As we move forward, we must continue to work collaboratively across sectors, regions, and disciplines to develop effective solutions that will safeguard our planet for future generations. At the end, I would like to thank all of you for your participation in this session as the last GARD 2023 session, and I look forward to meeting you all again in our next GARD 2024. Let us continue to work together to ensure a healthier, cleaner, and more sustainable future for all. And again, I'd like to emphasize not to forget that our actions today will shape the future of our planet and all those who inhabit it. Thank you so much for your participation. And I'd like to have everyone there and just take a photo with everyone, if Chelsea also is there, or any other participants.
Yeah, Barb, may I
Yeah.
say something? I just like, on behalf of GARD, I would like to extend our sincere gratitude and appreciation to your presentation. Your presentation is unique. You address the environmental issues, and we are very grateful to your time and to your talents. Thank you so much. And I hope you will keep getting in touch with us and be active for the 2024 GARD Forum. Thank you.
Thank you so much. And thank you again, audience and the speakers, for your participation. We'll see you soon. Take care.
Bye.
Bye.
Bye. Bye. Bye.